All right, so let's look at question 7 from section 1.5. So we're given a function for the velocity of a ball that's been tossed vertically. So v of t equals 16 minus 32t. So v is measured in feet per second, and t is measured in seconds. So we're also told a domain for the function. So the ball is only in the air for 2 seconds. So from time equals 0 to time equals 2. So when is the ball's velocity greatest? So a few ways to look at this, about it algebraically and graphically. If I know that my function looks like this, velocity equals 16 minus 32t. And we know that 0 is less than or equal to t, which is less than or equal to 2. Basically, as time goes on, our velocity is going to be constantly decreasing. So whereas our velocity is going to be greatest for the earliest possible time we have. So when t equals 0, we should have our greatest possible velocity. We can also look at this graphically. So if I were to graph this, what is this going to look like? So 16 minus 32t. So, we're used to looking at straight lines in this form, y equals mx plus b. This actually isn't that form. So I have a slope of negative 32. I have a y-intercept of 16. So the graph I'm going to draw here is not going to be, I'll try to make the scale as uniform as possible, but let's say that each one of these hash marks is 16. Actually, let's make it 8, so I can magnify this a little more. So here's my v of t axis. Here's my t axis. 0 for both. So 8 feet per second, 16 feet per second. And really did not need to make this that long, but that's okay. So we know that when time equals 0, what's our velocity going to be? Well, v of 0 is going to be 16 minus 32 times 0, or 16. So that's my y-intercept. V equals 16. We also know that we're only looking at 2 seconds here, so let's find some other values of v. 16 minus 32 times 1, and that's going to be equal to negative 16. And finally, v of 2 equals 16 minus 32 times 2. So 16 minus 64 is going to be negative 48. So we can actually need to extend this graph downward by quite a bit. And actually, I'm going to change my mind on some of these scales here. Let's say that each of these hash marks are each 16. So negative 16, negative 32, negative 48. And let's change our scales here on the time axis to units. So 1 second, 2 seconds. So at time equals 0, we have a velocity of 16 feet per second. At time equals 1, we have a velocity of negative 16 feet per second. And at time equals 2, we have a velocity of negative 48 feet per second. So I have 3 points here. And just to be clear, is it okay for me to treat this as linear? Is it okay for me to just connect all these with a straight line? And hopefully we can see from the form of this function that that is okay. We have an intercept, we have a slope. There's no other greater powers of t here. So this graph here should be linear like this. So our velocity graph should be a straight line with a downward slope, a negative slope of 32. So yeah, a lot of ways to answer this question, but the ball's velocity is going to be the greatest at the outset at time equals 0. What is the value of v prime of 1? So we're being asked for the derivative and told to justify our thinking. So we can answer this. Let's do algebraically and graphically again. let's go back and revisit our graph here. We're asked for v prime of 1. So we asked this question a lot, but how is a function related to its derivative? Especially when we're looking at a graph. I know that the derivative tells me the slope of a tangent line. So let's look at what the tangent lines are going to look like for function v. Well, v is a line. So what are the slopes on that line going to be? Well, they're always going to be whatever the slope of that line is. So what is the slope of this line? We said it was negative 32. And remember when we asked what the slope of this line is, we said negative 32. We didn't specify where, because you don't have to. It's a straight line. So maybe v prime of 1 is negative 32. So if you're not convinced by that, let's look a different way. So we know that v of t is equal to 16 minus 32t. We've talked a lot about the limit definition of a derivative. Let's use it. So in general, I know the derivative, a limit definition derivative looks like this. The limit as h approaches 0 of f of x plus h minus f of x over h. So let's start filling in, the details that come from this function. We don't have a function called f, we have a function called v. Its input variable is not x, it is t. So we have v of t equals 16 minus 32t. We're still going to have our little separation called h. So what's v of t plus h? That is 16 minus 32 times t plus h. We don't care about the derivative everywhere. We just care about the derivative here. So at one point. So what I want to do is this. I want to find the limit as h approaches 0 of v of 1 plus h minus v of 1 all over h. So what is v of 1 plus h? So let's take care of that here. V of 1 plus h will be 16 minus 32 times 1 plus h. So 16 minus 32 times 1 plus h minus v of 1. So we can plug in 1, then we also graphed it. We know the v of 1 is negative 16. So minus negative 16 all over h. And I forgot to carry the limit operator, so we'll squeeze that in here. So let's keep evaluating this limit to find this derivative. So let's expand some of these brackets. So I get 16 minus 32 minus 32h plus 16 all over h. So what happens here? It looks like all of our terms that don't include h cancel. 16 plus 16 minus 32 is 0. So I get the limit as h approaches 0 of negative 32h over h. The h's cancel. So what does that limit become? Negative 32. So a couple different ways here we got this value. So first, talking about this as the slope of tangent lines, or really the slope of a line. And using the limit definition of derivative, we still get negative 32. So justified our thinking from a couple different avenues there. What are the units on this value? So we got negative 32. So remember, a derivative is the instantaneous rate of change. So when we're talking about a rate, we have to be talking about two quantities that covary, two quantities that change together. So what are the units of those quantities? Well, the velocity is measured in feet per second, and time is measured in seconds. So feet per second, which is a unit you've probably heard before, or another way we can say that is feet per second squared. So I'm going to stick with this one. This will probably make this is a more common, probably more favorable way to say this unit, but we have feet per second squared. So what does this value and the corresponding units tell you about the behavior of the ball at time equals 1? So this is probably a good time to talk about what the heck is feet per second squared. What is that a measurement of? Well, we can talk about that by looking at this derivative here. We are given velocity with respect to time, and we took a derivative. So what does that derivative tells you? It tells you the rate of change of velocity with respect to time. So how does velocity change as time changes? And this is an idea in physics we call acceleration. So we kind of like relate all these ideas together. What is velocity? Well, velocity is the rate of change of position or displacement with respect to time. So that is a rate, but we can also talk about the rate of change of velocity with respect to time. And that's what we've just done here. We found acceleration. One more detail I want to point out is that this acceleration is constant. And does that make sense for something that's, under free fall like this is? We threw a ball into the air, and basically no other force was acting on it. It's just gravity. So we do get constant acceleration under gravity. So it does make sense that the acceleration we got here was constant. We were asked to find it at t equals 1 second, but the acceleration would have been the same for any time in our domain. And finally, question D. As usual, I got ahead of myself, but that's what that v prime tells you. So v prime of t is acceleration. So, and that's generally true for velocity. The rate of change of velocity with respect to time, that is by definition acceleration.